Okay, so things we got to remember about work energy theorem. Okay, first off, the most important part is that work is a change in energy, be that potential energy or kinetic energy. That's what it is. I'm doing work if I change the energy of something else. That is, I lift it further from the Earth's surface than it already was. If I lift it from the Earth's surface further than it was, what kind of energy am I changing about it? Potential energy. Okay, if I make it go faster, then I'm changing its kinetic energy. All right, so in any case, okay, I'm going to have work being equal to the change in, it's truly mechanical energy, but it'll be either potential or kinetic, which could mean then that I have like EK final minus EK initial. Everybody all right with that? Okay, oftentimes, one of these is zero. Agreed? Oftentimes it is. Not always, but oftentimes it is, which essentially then means that work is the final energy or the initial energy or whatever. Okay, and what's the other formula for work? Force times distance. Okay, so that's the other thing we got to remember. Most of the time, this is how it sets up. Force times distance is either going to equal 1/2 mvf squared minus 1/2 mvi squared, or it's going to be a change in potential energy where it's going to be force times distance equals m times g times h, final minus initial. Okay, everybody, is that ringing a bell for everybody? All right. Now, yesterday, we got started on this worksheet, okay? And by the way, I want to thank you guys for being really good and helpful to my sub yesterday, okay? So we have a force of 32 newtons that's required to lift a box 3 meters vertically against the force of gravity. If I'm working against gravity, what kind of energy am I changing here? Potential. All right, so they're telling me that F equals 32 newtons. And they're telling me what else? Distance, yeah, okay. Height is still a distance. It's a vertical distance, right? So don't get confused if it says height. Yes, this distance could also be the height, and that's fine, okay, which equals our 3 meters here. What this question is trying to show you is this. I could calculate the work done by going force times distance. Okay, well, when I do that, I'm going to go 32 times 3, which equals 96 joules. Or I could figure out that I lifted it 3 meters, which means I changed the potential energy of the box. That means I did this, m times g times hf minus m times g times hi. Well, they didn't tell me what hi was. I'm assuming it was where? Okay, on the ground. So then I'm going to take, I don't know what the mass of the box is, but I do know this force here. Okay, is that, what's this m times g? Does that equal a certain force? What force does it equal? Force of gravity, right? Well, it just said you did this against the force of gravity. So I can say that again, that 32, okay, the force of gravity times the height, 3 meters, is 96 joules. All that question wants to know is, if you do 96 joules worth of work, do you recognize that that changed the potential energy of the box by 96 joules? That's what that question's asking. Okay, do you recognize that work is a change in energy? Right? This wasn't about you being able to calculate force times distance. It was about the recognition that when you do this, this changes. All right? Now, I understand that there were some questions on the sheet that gave people trouble. True? Okay, which ones do we need to go over? Okay, don't be afraid to call them out here, guys. 3? All right, so we got Austin standing on the floor of the gym, jumps up to dunk a basketball. He has a mass of 70 kilograms and jumps straight up to a position where he has gained 800 joules of energy. So if you gained 800 joules of energy, would you have had to do 800 joules worth of work? Yes, okay. So our change in energy, okay, which is also our work, is 800 joules. That's what that's telling us. Okay, it's going to be one or the other of those, or maybe both. Okay, he has a mass of 70 kilograms. All right, what kind of energy is changing about Austin when he's jumped? Yeah, his potential, and yes, his kinetic energy changes on the floor. Okay, he's going to have to generate some speed, but we're only talking about how high he jumped. When he's at his maximum height, how fast is he going? 0, right? That's where he turns around, right? When I throw that up in the air, when it's at its highest point, that's where it changes direction and starts coming back. And It's not moving there. Okay, so what we know then is that his potential energy has changed. Right? He has none when he's standing on the ground. He has some when he's at his final height. We know the change in potential is 800. We know his mass, and we always know gravity. So if I want to calculate how high he jumped, his final height, I divide both sides by mg. Okay, comes over here, and then I plug in my numbers. 800 joules divided by 70 kilograms times 9.81. Now, when you punch that into your calculator, you do have to outsmart your calculator. Okay, that is, you have to enclose the bottom in brackets. Okay, 1.16 meters. Actually, is there 3 significant figures in that question? I think there is. Yeah. Okay, Thomas. Oh, no, because I gave it out yesterday. See me in a minute, I'll give it to you. Okay, other ones. Okay, so, sorry, that's number 7. Number 67, right here. Okay, rubber band has a mass of 0.02 kilograms, sorry, and all 320 joules of energy that it has is kinetic. How fast is the rubber band going? All right, so they're telling us its kinetic energy is 320 joules. They're also telling me its mass, 0.02 kilograms. And they're asking me to find V. Do I have a formula that has those 3 things in it? Yep. Okay, this isn't actually a work energy theorem question. It's just a kinetic energy question. EK equals 1/2 mv squared. It's kind of a work energy theorem question in that, where did it get this 320 joules from? Probably from me stretching the rubber band and then snapping it and letting it go, which I told you not to do in the lab. Okay, that's probably how it got all of that energy. Right? I did 320 joules worth of work on it at some point. All I need to do is calculate V. So I'm going to divide both sides by 1/2 of m. Bring that over here. Okay, and then what do I have to do to get V not squared? Square root. Okay, so I'm going to have square root of 320 divided by 1/2 times 0.02. Okay, so when I punch that in, okay, I'll have a square root of 320 divided by, well, 1/2 of 0.02 is 0.01. Okay, so 178 meters per second. Don't get in front of that. That's really fast. Okay, it's all fun and games till someone loses an eye, right? Okay, that would certainly take out someone's eye. Well, it doesn't have enough mass to do a whole lot of harm to you, but yeah, you certainly wouldn't want to. That would hurt. They would leave a welt, yeah, for sure. Okay, other ones. How far along did most people get? Anyone get like past number, let's say 10 on there? Okay, a couple of people. All right. Let's keep working on that for a while then, and we'll go through any more that kind of trip us up. I'll do a couple of kind of review examples here in a few minutes once we get attendance done, and okay, we'll go from there. So Sam is going to attempt skydiving. So he flies in a plane to a height of 1,250 meters. Okay, where are we measuring the 1,250 meters from? From the ground. Okay, so I'm just going to put in there that that's a height. I'm not going to indicate initial or final just yet. Okay, 1,250 meters. He has a mass of 55 kilograms. Okay, how much potential energy does he have? All right, it's not actually asking about how much work was done to get him there. It's just asking how much energy does he have when he's 1,250 meters off the ground. So I just go EP equals m times g times h, which is essentially force times distance. All right, I'm just taking his mass, 55 kilograms, multiplied by 9.81, multiplied by 1,250 meters. Okay, and that should give me 6.74 times 10 to the 5 joules. Yeah? Okay, how do I recognize that's all I had to do in that question? Okay, because it never gave me force in that question. So I knew I didn't have to do anything with work, okay, because it never gave me force. Right? It was just an energy question. And sometimes that's going to happen. Okay? That's why it's so important to write down your givens. As soon as I noticed force wasn't one of my givens, okay, I might have had work equals m times g times h, but I knew I wasn't going to have to use force times distance, okay, because it just wasn't in there. Right? And that's probably the biggest challenge, is recognizing when do I have to use this and when do I have to use something else. Okay, that's the challenge with physics. All right, any other ones? 12? Okay, walking a tightrope at the circus. Did anybody watch that guy a couple years ago who went across the Grand Canyon on a tightrope? That was crazy. Okay? And I watched it like after it had happened, and I already knew the guy was going to live. But it was like nerve-wracking to watch this guy, especially when the wind came up. I thought for sure he was going to fall. Anyway, okay, walking the tightrope at the circus. He has a mass of 80 kilograms. Okay, and has 8,900 joules of energy on the tightrope. What kind of energy do you suppose that is? Potential. I don't imagine he's running, okay, or moving really fast if he's standing on a tightrope at this point. Okay, so 8,900 joules. It mentions nothing about him being in motion. Okay, on the tightrope, how high is the tightrope? All right, so I'm looking for H. Do I have a formula that has M, EP, and H in it? Yep. All right, all I have to do is solve for H. So I'm going to divide both sides by M times G. Okay, and plug in my numbers. So 8,900 joules divided by his mass, which was 80 kilograms, okay, times 9.81. And again, you have to outsmart your calculator on that one and put the bottom in brackets. Okay, and when you do that, you should get it's 11.3 meters above the ground. You have one? 7? Okay, 7's a good one because I use questions like this on the unit exam all the time. Work energy theorem questions where I, bow and arrow or slingshot or something like that. Okay, so I use a force of 100 newtons and I pull back a bow 0.29 meters. What did they give me there? Distance. All right, I've got force and distance, so I know for sure this is a work energy theorem question. Okay, at what speed will a 0.120 kilogram arrow, so that's mass, leave the bow at? All right, if they're asking me about speed, what kind of energy are they most concerned with here? Kinetic energy. All right, so the work I'm doing in pulling back the bow is going to become the kinetic energy of the arrow once it leaves the bow. Everyone okay with that? Okay. So I'll have force times distance equals 1/2 mvf squared minus 1/2 mvi squared, right? Because it's change in kinetic energy. At this point, I've got to think about the situation I have. I have an arrow in a bow. I've drawn back the bow, okay? How much kinetic energy does the arrow have right now? None. It isn't moving. It's in the bow. All the energy is in the bow right now. It's potential energy. It's elastic potential energy because of the work I've done in drawing back the string. Everybody follow there? When I let go of the string, my part in this is over. Now, the bow will take the energy that it has and do work on the arrow by having the string push on the arrow, exerting a force through a distance and letting the arrow go. Okay? So, initially, this has no kinetic energy. So now I'm left with force times distance equals 1/2 mvf squared. That is what I'm looking for. How fast does it leave the arrow? Because once it, or sorry, how fast does it leave the bow? Because once it leaves the string, the bow isn't doing any more work on it, right? It's not touching the bow anymore. The bow can't exert any force. All right, so I'm going to divide by 1/2 of m. And then square root to get rid of the square there. So when I plug in my numbers then, 100 newtons times 0.29 meters divided by 1/2 times 0.120. Okay, should give me my speed out of the bow here. And again, this is one where you probably want to do it one piece at a time. 100 times 0.29. Okay, it's 29. Why did I punch that in? Okay, and then divided by 1/2 of 0.120, so that's 0.06. Okay, and then square root that. All right, so we get 22 meters per second as its speed leaving the bow. Okay, making sense? Okay, and like I said, guys, that is exactly like the kind of question I'll ask on a quiz or a unit exam. Okay, exactly like that one. Any others? Okay, how many people have done the whole sheet? Okay, a couple of you. Okay, this is the next thing that we're going to be talking about. Let's say that you're on a roller coaster. Okay, most roller coasters, with the exception of some of the more modern ones, okay, involve towing the train or the cart up to the top of the highest hill and then letting it fall down the track. Okay, so during the part where it's being towed to the top of the hill, what's being done? Work. Okay, force is being exerted over a distance, and essentially it's giving the roller coaster what kind of energy? Mostly potential, a little bit of kinetic because it's moving, but it's moving mostly at a constant speed. Okay, so let's say that up here at the top of this hill, we are 50 meters above the ground. Okay, and let's say, we're not moving very fast. Let's say we're moving at 3 meters per second, right, at the top of that hill. Could I figure out how much energy I have there if I knew that the mass of this cart was, let's say, 200 kilograms? Yes, I could. Okay? How do I figure out how much mechanical energy it has? We talked about this like the first day, so it's been a while. Right. I add potential and kinetic energy together. Okay? Mechanical energy is kind of the sum total of all the energy that the object has. Okay? So mechanical energy equals EP plus EK. And I can figure those two out because I know the mass, the speed, and the height. Right? So I'm going to calculate the mechanical energy here at the top of the hill by going 1/2 mv squared plus m times g times h. Right, so we'll have 1/2 times 200 kilograms times 3 squared plus 200 kilograms times 9.81 times 50 meters. Okay, and then 200 times 9.81 times 50. Okay, so we have 99,000 joules worth of energy at this point. Is that a lot? Yeah, it's a fair amount of energy. Okay, so I have 99,000 joules. How much mechanical energy would the cart have when it's down here? Okay, it's moving, so I've frozen it in time, and the cart's gone down the hill, and now it's at the bottom. How much energy does it have there? 99,000 joules. Okay, remember, all the work's been done by the time it gets to here. Now, this is the amount of energy this cart has at any point after that, unless more work gets done. Okay, but no more work is being done. Other than gravity, there aren't any forces that are forcing that cart to go faster. Gravity's just pulling it down the hill, right? Which essentially means all of this, the potential energy it has there, doesn't go away. It turns into kinetic. All right, so once I get down here, all 99,000 joules of energy is going to be kinetic. Okay, yes, mechanical too. Yeah, okay, but in one form only. Because down here, what's my height? 0, right? I'm assuming that this is down at ground level, so I wouldn't have any potential. I would have 99,000 joules worth of kinetic energy down here. So, saying that, could I figure out how fast the cart is going here? Yeah, okay. If I wanted to do that, I'd just have to recognize that according to the law of conservation of energy, the initial energy equals the energy essentially anywhere else, which would be by comparison the final energy. All right, so down there where it's all kinetic, okay, I now have 99,000 joules of kinetic energy. Right? And now I could calculate how fast that object is going simply by going dividing that by 1/2 of 200 and square rooting. Okay, so if I did that, Why did I actually punched that in? Instead of just taking off 2 zeros, I actually punched that in. That's just dumb. Okay. All right, so down there it's going 31 point, actually I think I only have 2 significant figures there, so 31 meters per second. Okay, pretty fast. Could I do the same thing if the cart was over here? Okay, it goes back up, but what if I told you that here it's 10 meters above ground level? Now I could do it. Okay, because I could figure out how much potential energy it has here, okay, and then figure out what is left. Okay, well, what's left is the kinetic energy, and from there I could calculate how fast it's going. Right, that's where we're going to be headed in this unit, is being able to do what we call law of conservation of energy problems. They all work the same. They all rely on you understanding that EI equals EF. Okay, your initial mechanical energy equals your final mechanical energy, which when you expand it out means this. Okay, it means the initial kinetic plus the initial potential has to equal the final potential plus the final kinetic. So as long as I can find the mechanical energy at one spot, I know what it is everywhere else. Right? Now, what am I assuming is true when I say EI equals EF? That it's a perfect world, right? And that no energy is being lost to sound, friction, heat, all that other stuff, okay? That no forms of energy are being wasted, which is obviously not true, okay? But we're going to say that it is, okay? The law of conservation of energy still holds true even in the real world. It's just EI equals EF plus all the work that I do against what are called non-conservative forces, friction, all the energy that I lose along the way. It's still accounted for. It just doesn't become mechanical energy at the end. You won't have to deal with that until physics 20. Okay? In science 10, we live in the happy-go-lucky utopian physical world where everything works out wonderfully. Okay? All right, finish up that sheet. We'll go over any ones that give you trouble. Okay, rest of the way here.